These days, you usually go through a process that's outlined in this slide, where we have whatever physical variables that we want to measure, like temperature, pressure, flow, etc. That's our physical system. I've denoted this by a little sine wave. You'll see why in a moment. And we take that and we try and turn it into an electrical signal. That wasn't always the case in the past, of course. I think if you go back to the mechanics lecture, you'll remember the little pictures of the spirometer, which was measuring change in volume. And those devices mechanically moved a pen with ink in up against a rotating drum which contained paper, and so it wrote the trace out on the paper. And for many years we used chart recorders, which were pen recorders, whereby the signals were connected and the pen moved across the paper and wrote the trace out that way. And to analyze those traces, you simply used yes, let people in, please. You simply used your ruler to measure what the trace was doing in terms of how big it was and how fast it was and so forth. Well, we have progressed many, many years beyond that to the system that we use these days that's pictured here, where we transduce everything from its physical change into an electrical change. Electrical because we can handle electrical signals very well. We have the mathematics to do it with, and we have devices that we can use to take the noise out of our signals and help us see what the actual signal is, because all signals have noise. It has to do with the fact that we operate at normal temperatures, and at normal temperatures electrons move randomly and they add to the electrical signal because they are negatively charged electrons moving around. So every signal will have a noise. Nice to get rid of it, yes, if we can, by something called signal conditioning. And we might also take out parts of the signal that we don't want. As you'll see, frequencies that are not necessarily useful to us. We may only be interested in a very slowly changing signal, in which case fast changes due to noise, we should filter those away. And finally, what we want to do is not write this out on a chart recorder anymore to see what's happening. We want to use an analog to digital converter, which then will be useful to provide a computer with a digitized signal. And digitized signals we can handle quite well. And indeed, part of the signal conditioning may take place in the computer itself, where we can do filtering and various other tricks of the trade. So that gives you an overall idea of the system whereby we can obtain our data and have a look at what it looks like on a computer. But there are various aspects of that we have to be careful about so that we see the truth rather than something that may be not actually related to what we're trying to measure, but due to the system of measurement that we're trying to use. So one of the bases of our signal processing these days comes from the idea that Fourier put forward. And he said that any repeating signal, any signal that keeps repeating, we can decompose that into a series of sine waves. And you might say, well, okay, respiration is a repeating signal. That's not too bad, but there's lots of signals that don't repeat. Well, if you take the chunk of the signal that you've measured and say, all right, that is the signal, then you can still decompose it into a series of sine waves using the Fourier transform. The Fourier said, you can take this odd-looking signal that seems to be randomly varying all over the place, but it does repeat over time. It is made up of a series of sine waves, and we've shown them here. And what you can do is to look and see, of those sine waves, what frequency are they at, and how big are they? And that gives you the frequency spectrum of the signal. Now, you can think about this if you are at all familiar with music theory, that this is the same kind of thing that we are dealing with when we ask an instrument to produce middle C, for example. The middle C is the fundamental or lowest frequency, which we see pictured here. And how do we know what kind of an instrument it is? Well, that may be the fundamental frequency of 440 hertz for middle C, but there are what we have called harmonics attached. In other words, there are other sine waves at higher frequencies. And those harmonics are what determine our recognition that it's a piano note. It is not a flute. It is not a trumpet. Because these harmonics, these extra higher frequencies than the fundamental sine wave, they are what gives you the characteristic of the instrument. So there we are. Very useful to say that we can take a signal and we can break it up into various sine waves. That's good too, because we know how to handle sine waves. Since the electrical revolution in history, we have been dealing with sine waves because our electrical generators generate sine waves. So what carries through the power lines to your house are sine wave variations in electrical voltage at a particular frequency that enters the house as 60 hertz in this country, Canada, but may be slightly different in other countries. So why sine waves? Sine waves are generated, if you like, by a rotating vector, such as a wheel rim point, such as a rotating generator being rotated by water power or steam power or some other aspect that makes the mechanical elements turn. And they will generate a sine wave as we see here. So if we followed the point here at the end of this amplitude arrow, as it went round this circle, we would see that it went in a sine wave fashion here. And so we talk about sine waves in terms of descriptors for them. This is the amplitude of the sine wave, and it's the amplitude, the length of the rotating vector here. Engineers, electrical engineers, all deal with rotating vectors because we have the mathematics to deal with them, and that's how we handle electrical signals. So we talk also about the phase angle of the signal. Where are we on the signal? Right here. At what phase is this? And that is the angle from 0 here. And we can measure that in degrees and go around to 0 to 360 degrees. I should have put a 360 here. Or we can talk about it in terms of radians. and the radians is the arc divided by the radius. And that goes to 90 degrees here, or pi over 2 in radians, 180 degrees, or pi radians, etc. around here. The other thing we talk about, apart from the size and the phase angle, we talk about how long does it take to go around this circle? How long does it take to go from here and generate the complete sine wave, one sine wave, the period of the sine wave? And the period of the sine wave defines the frequency of that sine wave, because the reciprocal of the period is the actual frequency. So that's where we talk about things like, the signal is out of phase. That means it's 100 degrees out of phase. It means that when we think it should be going up, no, it's going down. It's 180 degrees out of phase. So we use this idea of phase in our normal language as well. If we take a look at the kind of signals that we want to measure, we can determine sort of what the range of frequencies that make up the final signal. If we were looking at the Fourier series in the time domain, for example, of a square wave shown here in blue, we would have a fundamental frequency here in the thick red line, and then a whole series of higher frequencies at integer intervals that make up, when added together, a square-looking wave. And so the square wave has very, very fast changes associated with it. So you can think about any of your signals that have fast changes are going to have very high frequency components in them. And if you lose those high frequency components, then you will mush the signal so that it no longer looks like a square wave. And here's some of the examples where we go from the lowest to the highest sine wave that might be making up our signal. For ECGs, EEGs, which are electrical in themselves, blood pressure, which isn't, which we will transduce, 0 to 200 hertz, and so forth. Respiration, quite slow. Body temperature, very slow. Speech, for example, very fast. Our ears have to respond as transducers somewhere between 15 and 20 kilohertz. And as we get older, we begin to lose this high frequency components, and we don't hear the high frequencies as well. So we determine the frequency spectrum in the frequency domain and look at the lowest fundamental frequency and the highest that makes any difference at all to the signal. And this is what we call the bandwidth of the signal. And we may need to know what that bandwidth is in case of further processing. If we look back, let's go back to our thing here. We're going to transduce our sensors. And the transducer is probably the most difficult to deal with, because in some cases we have to convert things like, for example, the amount of CO2 in a gas. How do we do that? Well, we take a sample at the mouth by sucking it from down a tube, putting it into a very small chamber, and we shine an infrared light through it. And since CO2 absorbs infrared, a change in CO2 will alter the amount of infrared light that reaches the bottom of that little chamber, where we have a transducer that senses the light amplitude. So that's a complicated transducer. We may have something like a flow transducer, which when you blow through it, it provides you with a signal proportional to the flow. There are various kinds of things you can do that. You can put a little miniature turbine in it so that it spins, and we can pick up its rate of spin as proportional to the flow through it. One of the ones that we use commonly uses the flow through where there is a special kind of resistor, electrical resistor, that when we put a current through a resistance, we tend to heat it up. And then when we blow air across that, we will cool it down according to the flow. And so if we have a measurement of what the resistance is for our given current through it, it will change as we cool it or warm it with the flow through the transducer. So transducers are tricky to deal with and very important to know that they are working correctly. So we do various things to them. One of the things is an impulse signal, and we don't often use that as a standard test signal to see how our transducer handles it. Most of the time we look at something like a step change in the signal, and that imitates the sudden change characteristic of a particular signal that we might be interested in. The other thing that we do is we put in ramp signals because we want to know whether we have what we call a linear response. In other words, for the signal going in, how does it come out? And we also want to know how it handles that in time as well. And here's gives you an overview of the kind of things that we might get. If we have put in our input here, which is our ideal, what it should be, the output and input should be linearly related by this ideal curve of this straight line. But in fact, what we get out of it is this measured response here because of the way that the transducer works. We can fix this in our computer. If we know that it should be straight, we can straighten it out. So we can deal with that, but we should know that our transducer is not linear. What about how fast it can respond? Because it will have a frequency response. It will have its own bandwidth over which it can respond correctly. Going back to our audio idea here of looking at bandwidth, anybody that owns a hi-fi system may have said, "Ooh, mine is very good because it goes from a very low frequency to a very high frequency without changing the signal." And we would measure that here as the frequency response in the bandwidth. So in many cases, you will use transducers that go all the way down to 0, but they will certainly not go past a particular high frequency. We'll talk about that in a moment. But talking about the way that the transducer would respond to a step change, we would see that depending upon how good it is at the high frequency components of your signal, it will either respond very quickly and be almost a square, or respond rather sluggishly. And if it's a first order system, we characterize that by the time constant, and the response is an exponential. The response of the central chemoreceptors, for example, are generally thought to be an exponential response. Why is that? Because the central chemoreceptors are located in a volume of tissue, and when we provide a step change of CO2 in the arterial blood flowing through the brain, and therefore going to the tissue where the central chemoreceptors are, we would be filling up our tissue with the CO2 being provided from the blood. And we've suddenly changed the PCO2 there, but we don't get the sudden change at the central chemoreceptors. We get a sluggish change because it takes time for the tissue volume to fill up from the blood supply. And that time constant is roughly 100 seconds. For any of this kind of compartmental model where we know the volume of the compartment and we know the volume of the flow through it, then we simply divide volume by flow. And that's what gives us our time constant of 100 seconds for the brain. And indeed, when we measure the ventilatory response to a step change in the partial pressure of CO2, it is an exponential. And so that's a first order system. Some of your transducers may not be a first order system, and they may be a second order system. And a second order system has a natural frequency of vibration. And if you hit it with a signal that has one of its frequency components at that fundamental frequency of the transducer, it will ring like this, like a bell. And we have to damp that down properly so that we get something that does not ring like a bell. This is a problem for anybody measuring blood pressure clinically, because one of the ways of doing that is to attach a catheter, which is the insertion of a needle into an artery. We have a tube going to our pressure transducer usually, and that pressure transducer has a little diaphragm in it that the fluid-filled catheter, the volume is therefore steady. It's filled with water, so any change in the pressure pushes that diaphragm, and it does so as a second order response. And so that could be a problem if we have it bouncing a lot and we say, the nurse says the systolic pressure, this peak here, is very high. But in fact, the blood pressure itself is not too high. And so that's why you'll see sometimes people erroneously put in a little bubble. And the bubble, of course, is air in the catheter system, and air is compressible and it acts to damp down that signal. So we talk about second order responses and we talk about damping them. The bubble is the wrong way to do it. There is another proper way of doing it that is sold, but we won't go into that. But it gives you an idea that yes, indeed, some of the transducers systems that you use will be second order, and you have to be careful about this. There was an exercise testing system that tested the ability, it fastened to the leg, and it tested the speed with which you could kick your leg out. And the thing used to ring, and you'd get a false reading, and people didn't realize that. There have been cases of neuronal recordings with systems that were second order that produced false results too. So this is a rather pernicious problem that you have to be aware of. When we look at our signal conditioning, we know what our frequency response that we want to measure. And we determine that by taking the amplitude of the signal versus its frequency, and we find this kind of thing. You may have looked at specifications for high fidelity amplifiers and seen that they provide you with this kind of graph to show that yes, their system does not provide any distortion by amplifying one frequency component over another. It is flat. We would like it to be flat so that all frequencies between, say, 15 and 20,000 hertz are magnified by the same amount to drive our speakers and so that we hear it properly. The bandwidth and measurement here of the input and the output is usually measured by something that we've called gain. In fact, gain is a ratio of the power output over the power input, which should be constant over all the frequencies. But we've taken that term gain and used it rather loosely to say that, oh, it's simply the output signal size or amplitude divided by the input signal amplitude. That is, of course, not power output over power input. Power is proportional to the amplitude squared. So gain as a term is misused, but it's done so commonly that we talk about it. And that's why we talked about loop gain when we were talking about the respiratory control system. It really isn't loop gain. It's a loop sensitivity, if you like. Output over input is sensitivity. And so we may have to take our signal, which may be very, very small in its electrical amplitude. And so we will have to do something with that, and we may have to amplify it. It may, in some cases, be too large for us to handle it properly with the rest of our electrical components of the measurement system, and so we will have to attenuate it. And we have to do that to fit the voltage input of our analog to digital converter. And they will vary. Some of them you can set them to 0 to 10 volts if your signal doesn't go negative, or if it goes negative, it might be -5 to +5 volts or -10 to +5 volts. But whatever, you have to fit your signal into that. And you'll see why that is the case. If we want to filter to eliminate noise, i.e. unwanted frequencies, then we can use various types of filter. And if we looked at our amplitude at various frequencies, the frequency response here, we would see a low pass allows the low frequencies through but cuts off the high frequencies. High pass lets only the high frequencies through and cuts off the low frequency. So a lot of the noise is high frequency. You might want to use a low pass filter if your signal actually is down in these frequencies here. You might be wanting to measure only the rapid changes and not any slow drift. And so you might want a high pass filter to eliminate the low frequency of that drift. And band pass is often used as well because you want to do both of those things. And there's a band stop filter where you might say, I'm going to use that filter because I know there's an electrical machine in the room that is broadcasting a radio signal at 60 hertz or whatever it is. And I will want to stop that so I can filter the signal at that particular frequency. One of the things that used to be used in the operating room that caused a problem was the electrical cutters, and they were terribly noisy. Not so these days. How do we get our signal into the computer where we only have binary numbers? Well, first of all, let's start to think about what binary numbers are. We are very used to counting on a base of 10, but numbering systems can have different bases. Octal, for example, that has a base of 8. People usually use base 10 because we've got 10 digits on our fingers, both hands, and these are digits 0 to 9. And then when we go past 9, we have to move to the left, and so the next digit is the tens, the number of tens. And when we reach 99 there, we have to move to the next digit for the hundreds. That is the way that our numbering system works. But in the computer, we use the binary system because the signals are either on or off, or true or false, or there or absent in a computer system. The voltage is either high or low. So it's a base 2 system. There are only 2 digits, 0 and 1, like a light switch, on or off. So we start counting. We are at 0. We count 1. We have to, if we want to count 2, we have to move to the left, which is for the 2s, left again, etc., etc. for the 4s. And as we show here, this gives us 1. This would give us 2. If we had 1, 1, we would be counting 3. If we have a digit here, it would be count for 4. A digit here is counting the 8s. 1 here is counting the 16ths. If we had all 1s here, we would have 1, 2, 3, 4. We have 5. We would have 5, 2 to the 5th. And I'm not quite sure what that is. If we have 8, we have 256, etc. One of the things that I put in here is the fun idea that if you use your 10 fingers in a base of 2, then you can count all the way to a very high number, to 1023. So that's rather an interesting idea. So you don't have to limit yourself to counting to 10 on your fingers. You can count to higher numbers if you use the binary system for counting. So what we've seen is that, yes, we move from the 2s to the 4s to the 8s to the 16s for each digit. So each column, which we will label n, is moving left, is a binary digit, a bit. And so its value is 2 to the power of n. That's a 5-bit word. And some computer word lengths have names like byte, that is 8 bits. We started with home computers and computers in the lab more or less with 8 bits. And 8 bits can count to 2 to the 8th, 256. I think 1, 2, 3, 4, 5, 6, 7, 8, yes, 256. And then we wanted to count to higher numbers using a digital counting system, because computers store their memory locations and they are addressed by binary numbers. So the longer the length of the word, the more memory locations we can address. Initially, that's why memory on the computer was very limited as to how much memory you could have for storing information, for storing numbers. You can store numbers in their digital form. You can store them as integers, if you like. You can store them as whether they are true or false. You can store them as a decimal kind of number, like pi 3.14. We call that floating point storage of numbers. And so that's the way that computers work. These days, we're up to 64-bit word lengths in our computers, which can address gigabytes of memory. How do we convert? Analog to digital conversion. One of the major things to remember is the Nyquist-Shannon sampling theorem. The sampling rate that we use, how often do we take samples of the signal, must be at least twice the highest frequency component of the signal. That's why we need to break it down using Fourier signals so that we know where the high frequency components are. And if we want those and we don't want to get rid of them, we have to sample very fast. So here's an example of our analog wave and the digital result if we take the samples at the points indicated by these lines. And so this sine wave here, we would sample it and it would end up looking like this. And it sort of looks like a sine wave if we use our eye. If we take more frequent samples, it begins to look better and better. And at this kind of frequency of sampling, it looks more like the sine wave that we started with. So it's very important that our analog to digital conversion samples the signal at the appropriate frequency of sampling. The other thing that we have a problem with sampling rate is if we have an adequately sampled signal, as indicated by these dots, which, if joined together, provide us with what looks like the original signal, which is the actual line itself. And here is the actual line. But if we only sample it rather infrequently, as shown, but regularly and on a regular basis, then we end up with what looks like a very low frequency. This is called an alias signal. It is not really there. It's an unrepresentative. So aliasing is something we have to be careful about. This is why one would want to filter out frequencies in your signal that are higher than those that actually make up the signal you're trying to measure. Noise often has high frequencies in it. This is why you'd want to get rid of them. Because if you sampled those, you would find out, I have a very low frequency in my signal, which should not be there. That's going to distort it and lead me astray. So there we are. Aliasing of high frequency noise appears as a low frequency, which masquerades as part of the signal, but it is not there. So that's another thing that we have to be careful about. And this is why we use filters for high frequency noise. The other thing that we have to be careful about is how we quantize the signal. And this is where we go for why we would have to either amplify or attenuate our signal so that its variation goes plus and minus or 0 to whatever the maximum is within and fills the space of our analog converter, which goes from, say, -5 to +5. We would want to amplify our signal so that it fits into that. And if it is too small, then it doesn't vary enough, and we don't see enough of that signal in the quantization. And then we fit that in there. But if we take our signal and we measure it, and how often can we make what the digital signal is? If it's a 2-bit word, we really don't get a good signal out of it. If we had a 1-bit, it's either on or off. It doesn't look like our sine wave. Here's 2 bits where, yes, here we are sampling, and we have 2 levels of signal. And again, it looks kind of like a sine wave. But if we go to 4-bit, it looks quite good. If we go to 16 bits of numbers that we can put it into over this range of signal, then it looks very good. And only if we look carefully at it would we see the steps between each sample. So quantization is something that you want to bear in mind too. So you don't want to buy an analog to digital converter that only works as a 4-bit word. And so that's why you want to go to at least 12 or 16-bit. What kind of setup would you get for your data acquisition system that does the conversion for you? There are many ready-made systems like those pictured here. Here's AD Instruments, where you simply plug in your electrical signal, connect it to your computer, and lo and behold, they are on your computer. Even Hans Rudolph has what they call a smart lab, which converts some of the signals that you want in terms of pressure and flow and puts them into your computer. The other way of doing things is the way that I set up my laboratory when it was running, and that was to use custom hardware. So there are many ways of assembling a custom hardware system to do it. Quite a few manufacturers, one of which is National Instruments, which I have used. And you can see pictured here some of the devices whereby you can connect your signals, and these will do your analog to digital conversion. You can even buy little boards to make your own kind of system, or you can buy something that is in a little case like that. Whichever you choose, you end up looking at a computer screen which will display your data. And how do we do that? Well, National Instruments developed this graphical programming language software called LabVIEW. And it's based upon the idea that you are going to create a virtual instrument. And the virtual instrument, like any laboratory instrument, has a front panel with a display and various controls that you interact with. But behind that panel is something that is doing the processing of the signal. And so you split that up into what they call the block diagram and the panel diagram. It enables you to put any of these display things like meters and so forth, graphical displays of various kinds, switches, numerical inputs, etc. And then you can deal with them on a graphical basis. So that if you wanted to add two signals together, you have something that looks like an adding device here. And you can put them through various little modules that will do things to your signal. And it's a very easy system to use. Here, for example, is what we use for acquiring data in rebreathing experiments. It has a panel that looks like this, and I won't show you what is behind the panel. The setup panel allows you to calibrate, and here is where you're doing a rebreathing and displaying what's happening to various things. You can click on a control to make a mark. You can switch oxygen flow off or on. You can control what the O2 gain should be, etc., etc. So that is acquiring data using LabVIEW. But I can also use LabVIEW for other things. Oh, here's another thing that you can do with LabVIEW. You can not only acquire the data, but once you've got it, you can read it in and you can analyze the data. And this is something that will be familiar to Harrison. because it's the program that he's using to analyze his data. So you can take the data and display it whether you want to or not. You can turn the display on or off. You can do various things to parts of it, like fit an exponential. You have various other things you can do to hit on these switches to move data around and synchronize. So you can acquire the data, you can analyze the data. Here's another thing that we're doing these days, and we're looking at the signals from magnetic resonance imaging and looking at pictures of the brain in various ways. And again, this can be done with LabVIEW. And the other thing that the third thing that you can use it for is you can develop simulations, and you saw some of these, I think. But here's a breathing simulation that shows you the volume in this artificial lung system going up and down, and what is happening to various blood gases like PCO2 and so forth. And you can do various settings on the model and run the model. So it'll do simulations of model systems, which are also helpful for your physiological experiments, because they allow you to test hypotheses before you go out and try and get data to support them. And we're familiar with this. There's another thing. This is another LabVIEW simulation system. So that is the end of what I have to say about the acquiring and processing of data. There's obviously a lot more to it, but I would urge you to read further about this. And one of the things to keep in mind whenever you're measuring in an experiment, do not trust your apparatus. Make sure you test it to make sure that it does what you think it's doing. So be skeptical. That's the same that you would be about any of your theories about how things work physiologically. Be skeptical, of course.